Okay, hopefully this is starting up. Not con Can't confirm that it's live yet, so just making sure I'm checking the technical things. Hello, is this coming through? Because again, my system is saying it's still like going live. Is this actually coming through? I know there's a bit of a delay on this, so let's see if this is actually working or not. Yes, it is working. Okay. All right. That's going to weird me out since that's still got like a processing thing, but yeah. So we'll see if we get some more people on this. But basically, I wanted to have a bit of opportunity to go through some of the things that I thought went well about this lever experiment, some things that I probably do a little bit differently if I had another go at it. I'm fairly happy with the results overall, and then I'm hoping that there's questions of things that I went through in the video, questions about other things that we might do on this channel, so other ideas for experiments. So it's going to be pretty free form. I don't have all that much planned for this, so hopefully if we get more some people in the chat asking questions, those would all be great. So a couple of things that I wanted to talk about that have already come up in some of the comments. So let me just kind of talk about this, what the video is first. So again, for anyone who hasn't actually watched the video yet, basically this experiment was a lever experiment where we had a bar on a fulcrum, and then the basic idea was I launch a car at one end of the bar, and it hits that bar, and then launches the cart on the other end of the bar. And then testing out what happens if we have this in different configurations, what happens if I use different masses at different distances from the lever, what happens in all those cases, saying things like, do we get conservation of angular momentum? Because the standard kind of textbook predictions of physics would be that for this kind of a system, if we have any system where there are no external torques acting around this fulcrum point, then the total angular momentum of that system should be conserved. Now, when one of the carts hits the end of the track, there's going to be a torque, but that's internal to the system. We're measuring how the motion of the cart changes, how the motion of that bar changes. When it hits the other cart and there's two forces, one acting on the cart and one acting on the bar, the torques that are generated by those forces are internal to the system. Since I've tried to minimize any friction on the tracks, and we're looking just before and just after the collision, and there's very little friction on this fulcrum point here, well, to a fairly high accuracy, we can say that, well, there aren't any external torques acting on this system. And therefore, if there aren't any external torques acting on this system, we should be able to verify that the total angular momentum of this system is going to be conserved. And that is independent of what masses we use at what distances, whether we have the spring bumpers for something closer to an elastic collision, or we use the clay for something closer to inelastic. Again, neither of them are perfectly elastic or perfectly completely inelastic. And even I changed out this bar for a more flexible bar, and the fact that the bar flexes also didn't have any effect on the on that conservation of angular momentum idea. So when I went through the data, again, I went through 26 different trials, in each case using a variety of different masses at different distances, different bars, whether I'm using the spring bumpers or the clay bumpers, that has an effect on the system. But when we were looking specifically down here at the angular momentum before the collision and after the collision, in all of these trials, we got very, very good agreement between these two different properties. I went through, and of the 26 trials, 22 of them, the percent difference in the angular momentum before and after was less than 5%. And exactly half of the cases, the error was less than 2.5%. So, yeah, that was the basic idea of the experiment. Again, I was pretty happy with how it went overall, and what I want to do is just basically open this up for questions. So as questions start getting added to the chat window, we'll go through each one of them. Again, there are some things that I thought went really well with this experiment, some things that I'd probably do a little bit differently. Some of those have already been mentioned in comments. So yeah, let's talk about this. So one of the comments that just came up is, there's a complaint about your prediction about losing half the velocity would only be relevant to an unelastic collision. Just checking, did you mean half the energy or half the velocity? Because yes, in the elastic and inelastic cases, I'm going to make an extra trial on this just so we can kind of change some numbers on this, so we can see what the predictions are. So if I copy this, we want to create another copy. Sure, something like this. So yeah, if I just set up some case, let's just start with one of these sheets from scratch. Then yes, whether we get the how those carts are going to move absolutely does depend on whether we have something that's closer to an elastic collision, which I was going for with the spring bumpers, or if we have an inelastic collision, something closer to clay where the object sticks on. That shouldn't be relevant because we test both of those cases. We have cases that are very close to having we have cases very close to matching the completely elastic case when I was using the springs. And in the clay case, well, we lost a lot more velocity. We didn't lose all the velocity because I admit the clay was not making as completely inelastic a collision as I was hoping it would. It wasn't fully sticking to that lever. And this is something that I'd like to kind of play around with in a future video. That if I want to have a system where it actually sticks to the lever, I'd have to change around some of the setup of the cart, because by the time it actually hits, in that sticking, it moves a little bit. So it's actually going to rotate, and that produces some side-to-side forces. So there's a question that came up, why didn't I use Velcro instead? Well, the Velcro, as soon as it hits, as soon as that bar starts rotating, there are side-to-side forces. And this track doesn't allow for side-to-side forces. If side-to-side forces were applied, well, that would apply an external force on this cart. Okay? And if there's an external force, then our angular momentum is if there's an external torque, if there's an external torque, then the angular momentum is no longer going to be conserved. So in this particular setup, rather than trying for getting exactly an elastic collision, maybe by using magnets, or an exactly inelastic collision, maybe by using a larger bar and changing the setup so it actually Velcro to it and could actually rotate, those are things that I would like to try in future videos. But the point that I was trying to make with this video isn't that I've got a perfectly elastic and a perfectly inelastic collision. The point was that no matter what kind of collision I have, if there are no external torques, the total angular momentum should match. Now, as part of this, it is still worth going through what is our elastic case and what is our inelastic case, completely inelastic case. Because those give us bounds on, if I do any actual physical collision, our results should be in between those two bounds. If we have an elastic collision, so using the springs, then the velocities we get should be closer to that elastic case. When we change to the inelastic case, again, it's not as close to the inelastic case as I was originally hoping, but it's definitely moving in that particular direction. Okay. So, yeah, I was never claiming that this particular setup will get exactly an inelastic case. I was saying it would be closer to that elastic case, that inelastic case when I'm using the clay than when I'm using, say, the spring bumpers. And going through these trials, well, we demonstrated that all of these trials, for both the spring cases and the clay cases, all of these trials we got velocities that were in those expected ranges for both cart 1 and for cart 2. We did not have a single case that was outside of this range of what classical physics predicts. So another thing about using the Velcro, and this is something that I would like to again expand on in a future video, probably a while later, because I'm kind of good on playing around with levers for at least for the moment. One of the things that would really help with getting the inelastic case would be to have a more heavier lever. Okay? The lever in this case, I wanted to make it very, very light, so that any measurement of the angular velocity of the lever, it does have an effect, but it's a minimal effect. So if I change this angular velocity of the lever and see what effect that has on the percent difference for both the conservation of angular momentum and the conservation of energy, if I change this from, say, 0.8 to, let's say, 0.6, it changes it by a few percent, but not very much. If the lever were more massive, then this angular velocity measurement, we'd have to measure that more precisely, which we can do, but again, others would have probably cried foul if I was using a heavier lever. So that was, again, there's a lot of kind of decisions that I had to make in setting this up, in saying, what are the key things that I want to demonstrate, and what's going to be the most direct way of getting there. And the thing I really wanted to demonstrate was this conservation of angular momentum. Okay. So a question, didn't your model claim that the same mass, same velocity would lose half the velocity of the outgoing cart? Yes, for the same mass, same velocity, if I go back to this one, if it's same mass and, well, I guess some initial velocity, then in the inelastic case, it should be when the cart sticks, so same radius. When the cart sticks, as that object rotates, it should be going with exactly half the velocity. Another way that I was thinking of setting this up, and this would probably be better for the inelastic case as well, is instead of having the lever and the second mass just able to freely move on the cart, just attach that second mass to the lever itself, so it can't bounce off. So we get guaranteed that that one stays stuck to the lever. But again, that would have required a much heavier lever, and I didn't want to add that into our into the complication for this one. Like I said, this is one experiment, lots of trials, and again, my goal with this was looking specifically at that angular momentum value, not specifically getting exactly an elastic and exactly an inelastic, but still using those cases as, here are the bounds that we expect to have for our expected ranges for these carts. Hope this is okay to ask, but in the original discussion, you were talking about inelastic collisions. Well, in the original discussion, it was very, very unclear of what was being requested. because what was being requested was the claim that when a cart runs into a lever, a cart that has double the mass at half the distance, when it ejects the second cart, that second cart should be going twice the velocity of the original cart. But the model that was being used to predict that, saying, oh, linear momentum, in fact, not even linear momentum, but the magnitude of those linear momentas should stay the same. So if I've got double the mass at half the distance, and I launch the other cart that has half the mass at twice the distance, so I think I said that wrong. If I have double the mass at half the distance, and that hits a cart with half the mass at twice the distance, since it's at twice the distance, it should be going 2 times faster, and if it has half the mass, that should be twice the energy. Well, when we did that trial, this was the trial for twice the mass at half the distance during that impact. And our ratios of before the trial velocity to the velocities after, in the elastic case, they were pretty close to matching up with what we were expecting. Okay. Only 10% off for cart 2. All the cart 1 values, since these are really close to 0, they do have these exaggerated percent errors, and we're not even worrying about the elastic case for this one, so that one doesn't even matter for this one. But we got pretty good agreement with what actual physics is suggesting. And there is definitely no doubling of the velocity. No doubling of the kinetic energy. Okay. But regardless of that, we still have this conservation of angular momentum. And that was true in both of these trials. The second trial was even a little bit of a better match. Again, there's always going to be variation between these different trials. But again, what we measured was only about 7% off in terms of the velocity of what we were expecting for cart 1. So we also went to the 3 times the mass at 1/3 the distance. Again, the alternative model, I'll just kind of leave it at that. The claim that was presented to all of us was that, if it's 3 times the mass at 1/3 the distance, we should get 3 times the energy output. Okay. So this is the elastic case, 3 times the mass at 1/3 the distance. Again, this smaller distance is harder to measure super accurately, so we were limited by that a little bit. But again, we get a pretty good agreement with what physics from a physics textbook predicts. We definitely don't get any sign of any increase in energy in any of these cases. Whether it's the elastic case, whether it's the inelastic case, no matter what masses we're using at what distances, in none of those cases did we ever get an increase in kinetic energy, in the total energy of the system. And in none of those cases were our measured velocity ratios outside of the expected ranges. Whether we're using springs, whether we're using clay for the bumpers, whether we are using one of these mass and distance ratios that seem balanced, like 3 times the mass at 1/3 the distance, we did other trials that did not have that kind of balance. So this was equal mass at half the distance. Again, we got very good agreement with what physics predicts. And as far as I'm aware, there was no prediction, not even as far as I could tell, not even a way of making a prediction using the, again, alternative model to ordinary physics. So again, those are some of the things that I want to point out. One thing that I wish I would have done differently, one thing that I wish I would have, a case I wish I would have done, is instead of having twice the mass hit at half the distance and launching the cart, I wish I would have done a case where it was a 1 mass. Here, let me kind of map out this case that I wish I would have done as an example. A 1 mass where the second mass is the one that's twice the mass, and that one's at half the distance. So cart 2, the one being launched, is the one with twice the mass at half the distance. Because, again, the alternative model that was kind of mentioned would have predicted a significant decrease in the total energy of the system. Again, using that erroneous model of using linear momentum instead of angular momentum. And yeah, I kind of wish I would have done that example to show that, no, in the elastic case, the energy is still very close to being conserved. It's not creating energy, it's also not destroying energy. But I only thought of that example as I was kind of finishing up the editing, and I'm good on levers. I did 26 trials of this. I'm good on levers for the next little while. I want to do... I want to do some other experiments, and if there are any recommendations for experiments, I've got a couple of things lined up, but those are some things that I want to quickly mention. And again, in all these cases, going back to again that alternative model of saying, oh, it's the magnitudes of the linear momentas that matter. In any of the cases where our R values don't match. In fact, let me pull up the... Sorry, I want to switch this around because I don't want to accidentally show something on the screen that has private information. Yeah. Where do I have the experiment for that? Sorry about this delay. Okay. So this model here, saying we've got this conservation of angular momentum. In the case where R1 and R2 are the same and the bar is of negligible mass, in that particular case, let me move this around a little bit so we can see both simultaneously. In that particular case, you might, again, think that the original mass times the original velocity, mass 1 times the velocity before the collision equals mass 1 times the velocity after the collision, mass 2 times the velocity of object 2 after the collision. In the case where those radii are the same, you might erroneously think that, oh, this magnitude of the linear momenta is matching up, that might have some merit to it. But that is immediately discarded as soon as you have any case where those R values are not the same. If those R values are not the same, which is, again, the majority of cases, you're not going to get that linear momentum, especially the magnitudes of the linear momentum. They are not going to match up. You can go through the data yourself and check any of these, but yeah, that model does not match up with experiment. And when we're doing physics, when we're doing science, the whole idea for science is we are going to build models of nature that are able to make predictions about the outcomes of experiments. And then we test those. We have to test those ideas. Until we test those ideas, any model that's proposed is simply a claim. And claims aren't evidence. I'm actually finishing putting together some notes on a video that will come out next week on claims versus evidence, and go into more of the details, go into some thoughts on this. But again, claims are not evidence. If you want to say that you have a model that predicts some phenomenon, you have to actually use that. You have to actually get data to support your claim. You have to demonstrate that it actually matches up with experiment. That's what I try to do, at least in these 26 different trials. For anyone who wants to test out some of these ideas, there's the data. It's again available in the videos. I try to put in chapters so it's easily defined. But you can check the numbers yourself. Check to make sure that I'm not cheating with these measurements of initial and final angular momentum. Make sure that in the elastic cases I'm not cheating with these measurements of the initial energy and the final kinetic energy of the system. So there's another comment. Notice the bearing for the carbon Dorado is different. The setup that I had for the carbon rod, I found that in the other holder that I had, I couldn't really get it fixed in place very well. It was also kind of thicker. So in this direction, when I was trying to do the hits that were close to the bar, if I had that holder that I previously was using, this track was so close to here that it was interacting with this. I couldn't anchor it in place. It was causing a couple of headaches. So I put together this other setup. It was basically a pulley. Let me actually quickly grab this. You know, I've taken this apart, but basically it was a pulley, and I took the carbon fiber rod. This isn't the same one. This one isn't the one that has the spots on it. But basically, I just fixed that to the pulley on one side of the pulley. I don't have the kind of equipment that I need to actually drill through this rod, but just to kind of highlight this, even if I would have drilled a hole, been able to drill a hole, like had the equipment to drill a hole through that pulley and put this on top, where the thing hits is not directly exactly centered on that axis. So putting on this side and saying it's hitting on this side, that leading edge is still really close to that pulley. It's still really close to that center axis. So those few millimeters that it's off by, I wasn't very concerned about that one. It would cause a tiny, tiny change in this moment of inertia, it not being exactly centered on there. But again, that would be like a 1 or 2% error on this moment of inertia of the bar. And as we kind of looked at, the moment of inertia of the bar doesn't have a significant effect, doesn't have a very large effect. It's already at like changing it by a couple percent, so that would be like 1% of 1% error. Okay. And yeah, I encourage people to try this experiment themselves. This one took quite a bit of effort to do, especially since I basically had to do it twice since my computer failed for the first one, and then some people were requesting changes on it. So again, I did try to put a lot of effort into this, and I hope that I presented a reasonable case for this idea of conservation of angular momentum. A couple other things. Again, I'm just waiting to see when more questions come up, because these questions are great so far. For these percent differences, there are different ways of calculating whether you want percent difference or percent error. And this is something that I kind of went back and forth on, figuring out what is the best and most reasonably accurate way of identifying when we have how much errors we're dealing with for these velocities. And in the case where we have, let me switch one thing around here just so I can pull up something to write on. Do this now. When we have a percent difference, that's when I don't have a really good, I'm comparing two values, but I'm not confident that one is the true value and the other one is less reliable. I don't have a high reliability on either one. So the percent difference is usually the magnitude of the difference over the average of the two quantities. Whereas percent error is, let's say I'm doing an experiment, I have a particular kind of measurement, I have a particular measurement. Sorry, I was just reading a comment there for a second. For percentage error, we're saying I have a particular measurement from my experiment, but I've got a different value, an independently measured value, that I think has a much higher reliability, a much higher confidence in that. So the percent error for this would be the difference between your true and expected values divided by the true value. Okay. So I went kind of back and forth on which one to do, because in these values, like I said, I wasn't really expecting to get a perfectly elastic collision or a completely inelastic collision. So I wasn't really expecting to get that, which is why I went with the percent difference rather than the percent error. The problem with that is, in this percent error value, let me pull that screen back up. Let's say I'm measuring two values. Let's say one value is 0.5. Let's actually make it really small, so 0.05, something like that. Something very close to 0. And let's say the value that I actually got was negative 0.02. Well, that negative, when we take the average between those, let me change this to negative 0.03 so the average is easier to do. The average between those is 0.01. So if I take the difference between those, which is 0.08, divided by 0.01, and then multiply by 100%, this would give me 800% error. When I have two numbers that are straddling 0, a positive number and a negative number, this percent difference calculation, it gives you very, very high error values. And what I was trying to kind of emphasize in the video is that when we get these completely different directions, yeah, these values that we're getting here, especially for the cart 1, which is going to be moving pretty slow after the collision, and again, sometimes moving forward, sometimes moving backwards, this is where we just expect to get ridiculously high errors on this one. So again, for the measured versus the inelastic, when we do that difference divided by the average between those two, this gives us ridiculously high percentage errors. I think instead, if I were to do this again, one of the things that I would have done instead is make a measure of where in between the perfectly elastic case and the completely inelastic case, where did our measurement fall for these cart velocities? You know, you can make a measure like that and scale it so 1 would be it's exactly the elastic case. 0 would be it's the exactly the inelastic case. And if I was outside of that range of 0 to 1, we would know, oh, that value falls outside of the expected range. That would be disconfirming evidence for this physics model. It would be a way of disproving that model. Again, we didn't get any cases where we had any cart outside of this expected range, but you know, I might actually put together a shortened version of this and just have trial analysis, and just, you know, really go through those quickly, because I know this video is very, very long. And I might put in a variation on the analysis like that. Since again, I know the video is very, very long, it got a little out of hand, but I did 26 trials, so. Okay, so comment, playing devil's advocate, all right. Think there's a claim that by adding clay, you ensured the free kinetic energy should appear and is absorbed, and basically I cheated it. Sure, that's the claim. Yeah, the clay was there to make sure that the carts were equal mass. There wasn't very much clay on there. I think maybe like 20 or 25 grams in total in the most extreme cases. Even for some of the carts where the masses weren't exactly the same, generally, instead of just using clay, I put extra masses on top of it. So you can actually see these masses down here. Of course, there's something that the claim is off, but yeah. Like I've said before, well, basically, I am no longer interested in his commentary. He's demonstrated himself to be dishonest, and I'm just literally not interested anymore. I do want to apologize. I did kind of block him from the channel. Again, just some of the stuff that he was coming out with recently was the last of a great many straws. And again, if he can't honestly, you know, be an honest interlocutor and keep away from just slurs of insults, then I'm just not interested. But I do apologize to those of you who were, I do apologize to those of you who had comments up in one of those chains. Those apparently got removed. My apologies for that. So again, my apologies for anyone who was involved in a conversation that got removed for that. So the hard elastic collisions, I played around with that a little bit. I basically put some rounded screws on the end of these carts, but what I was getting from my results was pretty much the same as using the elastics. And in order to affix them to the fronts of the carts, I was having a hard time doing that as well. Again, I don't really want to drill into these carts or do anything like that. So trying to get those metal pieces attached, I had to kind of put clay around it to hold it in place, but that would lead to another kind of issue with the clay thing. So I figured the springs would be the best case for that. Again, in future experiments, one of the things that I'm thinking of doing is setting up doing an experiment with like a giant Newton's cradle. So try to make one as large as possible so we can actually do those unequal mass cases, look at how momentum as a vector is conserved in those, and how energy is conserved. So yes, I did try setting it up in that way, but like I said, there were other complications, and it wasn't really seeming to give a whole lot better results probably because of how I was trying to affix it to that, how I was trying to affix it to the carts. Again, in maybe a couple of months or maybe in the new year or something like that, I'd love to do another experiment like this where instead of maybe using a lever, use like a wheel or something like that. And then have something on the wheel where something can come in, hit it, and bounce off, like a more of a swing thing like that. But again, I'm good on levers for at least the next couple months. There's other stuff I'd like to be doing instead of that. But again, I'm always open to ideas on what other things to try. Always like hearing constructive criticism and feedback, and yeah, I do value that, because again, that's part of the scientific process. That's part of what I want to emphasize in this channel, using the best methods and trying to test your ideas in as accurate a way as possible, and then seeing if the models that you're proposing actually match with experiments. So, okay, other questions about these? If I'm looking over here a bit, my dog is in the corner over here, just making sure that she's doing okay. She actually did make a tiny little cameo for about 5 seconds in the video. Just as I'm waiting for comments, I'll let everyone see the dog. Shameless using my dog as a prop to, just be cute on here. So, Yeah, she did get into the video. I didn't notice that she was in the background of the video for like, just a couple of seconds until later on, but yeah, she's cute. But anyway, so again, any other questions or comments? Ideas on other kinds of experiments to do. Some of the things that I've got coming up for this. Like I said, I'm just finishing up writing, and I'll probably record it today or tomorrow, a video on the difference between claims and evidence. Again, highlighting a couple of key things there. I'm planning on doing a video having to do with the buoyant force, Archimedes' principle, and putting some ideas like that to the test, including how Newton's third law applies to buoyant forces. There's a bunch of others that I kind of have on my short list, but if there's any other ideas on topics that people would like covered, then as always, let me know. Either in comments, again, I try to read a lot of the comments, or my YouTube email is listed on the About page. But any last questions before? Otherwise, we'll call this good for today. Again, I don't know exactly how long the delay is, but if anything comes up as I'm kind of making these closing remarks, we'll just keep going a little bit. But as always, thank you for the view. Appreciate the support that a lot of you have given, and especially appreciate it when there's ideas on new kinds of experiments, ways of improving those experiments. Especially some of those of you who have done your own experiments and tried that out. That's always great to see. I want to encourage that with my channel as well. Again, don't believe me. Don't just take what I say and say, okay, I guess that's right. Look at the evidence that supports anyone's claim. Whenever anyone is making a claim, you always want to ask, what is the data that actually supports this idea? And the best way of doing that is, the best way of doing that is actually trying the experiments for yourselves and learning these methods of how do we actually test ideas and apply this scientific critical thinking. But again, thank you as always for the view, and have a good rest of your day.